get into session 2. Our first speaker will be Jose from the Systems Group, and he's going to talk about Semantic SQL Queries over relational data.
Perfect. Just one comment. My name is Jose, not Jose. Did something happen? Hello? Where's my presentation? Okay. That's what happens when you move the cable. Okay. Sorry. So that's one thing I spend my life doing, is correcting my name. Because I'm Portuguese, I'm not Spanish, and unfortunately there are a lot more Spanish than Portuguese in the world. So, as Bart was saying, I'm going to talk about demonstrating semantic SQL queries over relational databases using an AI-powered database. This is some work that's been done at IBM Systems, particularly on the system Z, and which is the group I belong to. This group is led by Elpida Tzortzatos, and she's also in charge of the machine learning capabilities for the Z system. We are implementing this work, which is being developed and researched at the TJ Watson Research Center by Rajesh Bordawekar. Okay. I'll start our work by saying that it's one of the comments that they initially started is to try to obtain the information from a database without necessarily using the direct relationships that exist in the data, and then apply those to SQL queries and enable users to use the modeling of the database that way. Okay. I'll start by describing what AI-powered databases are. I will talk about the vector embedding approach, which is part of the techniques that we use to do the modeling of the database. And we'll then show how those models are used within the to design cognitive intelligence queries. Okay. We've implemented this system on Z using Spark, and we actually have implementations on other platforms, but for the purpose of demonstration, we use our Spark implementation on Z. We'll show how we model a relational table and how the model is created from that relational table. And we'll describe a little bit of the types of SQL queries that we have implemented to demonstrate the capabilities. We'll then go through a case study where we use the state of engineer expenditures as a transactional system. Even though we have several systems in-house, we usually cannot use the client data, so we use an outside public source, and this data is available online, and anybody can download. And we'll show on this database the results of some of the queries that we've implemented, including some of the explanation of these, the quality of the queries themselves. Okay, and then we'll finalize my talk with some final comments. Okay, just a remark: there is an IBM booth on the outside the conference. Actually, I think it's on my right. And there's going to be a small demo there of a video that shows the use of these capabilities on an example that we put together to demonstrate the work. So what are AI-powered databases? Okay, they are neural network models that capture the semantic information that's embedded in the relational database. That capture is represented within a embedding model called DB2VEC, and the purpose of this model is to capture the relationships between the different entities within the database. Once we have this model, we can then use them in the SQL queries to extract information off the database that wouldn't necessarily be obvious using the current techniques. Okay. As I've said before, we implemented this system in Spark on System Z, both ZOS and ZLinux, as well as on the Power Systems and x86. Okay. And my talk, I'll use a public data set as a demonstration. The vector embedding approach uses an unsupervised neural network, okay, that captures the meaning of the words as a collective contribution of the words within the neighborhood for each row of the table. Okay. It generates a model which is a representation of each word in the table as vectors, and then we use those vectors and the cosine distance to build up on the different SQL queries. In particular, we use semantic similarities and build on that in order to build up on the different types of queries that we implemented. Okay. And this work is based on the concepts of word embedding, where if you have good embedding within the vectors, okay, you can get a relationship between two vectors that mirror the linguistic relationship that exists in the words. Okay. So, for example, if you have a vector that represents the word apple, okay, a single plural relationship ends up being represented within the vector space as a subtraction between two vectors. Okay. A similar relationship ends up being a cosine relation between each vector. So rain, snow, and sleet are very related to weather, for example. Okay. We can also find dissimilar relations and analogy relations, and I'll show you some of these examples later on. Okay. The key point is that we want to mirror this data relationship that you see in the words as well within the database, within the contents of the database. Okay. As I mentioned before, once we have the model, we then build up on SQL queries and that use that model, and the way you use the model is through the user-defined functions or UDFs. Okay. And here is an example of a very simple UDF that is finding vendor names, and vendor names are any entity that made a transaction with the state of Virginia. The only reason it has vendor name is because of the name of the column. But for any entity, that's essentially the SQL query that we built, and the UDF is this proximity vendor name, is the one that calculates or uses the model, the AI model, to find the similarity between each vendor or between any vendor within the table. Okay, and we'll have some results in a little bit later. So, as I mentioned before, we built a new class of SQL-based semantic queries. These capabilities can be used for similarity, dissimilarity between entities within the database. Okay, they can be used for all lab type queries, grouping, and reasoning queries, and they are designed to be used within any normal, within any normal SQL program that any person can use. This is basically what we. Let's see. I know how to use this. Maybe not. There. This is a flow diagram of the process. You have an input table, which is the source data. That data goes through a process, feature engineering, and textification, and I'll talk a little bit about that later. Okay, that becomes the input to the generation of the model which is we call the vector embedding. Okay, that that model is then read into Spark as a data frame, as well as the data source. Okay? Those two are then input to any Spark SQL query that you build, okay? Which, if it's going to use the model that was created here, okay, then we use our specialized set of SQL queries with UDFs. Okay? It goes through the normal processing of a SQL statement, and it generates a Spark data frame with the desired outcome. Okay? Why do we use Spark? In particular, from a Z standpoint, well, first of all, Spark allows you a common framework for, and it can work in different platforms. With respect to the Z, the one important part is that we have different types of data sets, and we want our Spark implementation has a common input data that allows different databases to be fed into the system in a seamless way. Okay, that it was essentially designed because a lot of our clients, some clients have files in DB2 or VSAM, CSV files, and so forth. And we have that flexibility of supporting all these different types. All these different databases. Okay. Now let me describe a little bit of the data. The DB2 VAC and the context. So this is the actual data of, actually slightly changed, of the data of the state of Virginia. Okay. And in this particular case, we actually added 2 columns, and I'll explain why later. But the basic meaning of capturing the context for the DB2 VAC for our model is that every single entity, okay, within the table, for each row of the table, is considered a neighbor to the primary key of within the table. Okay. For the other columns, we then apply the meaning of neighborhood, very similar to the word VAC does, except that the neighborhood ends at the end of the row. So, for example, agency is related to its neighbors within this row, but it's not necessarily related to the neighbors on the next subsequent rows, at least from a direct standpoint. Obviously, if in this particular case, because they deal with the same agency, then you have a relationship that transcends the rows. Okay? This is what the data set looks like before we do any change. Okay, and I have a little bit of an explanation of the different columns. The way the data comes in is most of the data related to the state is represented as keys. Okay, and the way when you do the SQL query, you can then join with the different tables in order to actually get the names, so you have the meaning of what these keys mean. Initially, the data was broken up in quarters, and then we were trying to build the data, our data set for 1 year, 1 year's worth of data. We ended up adding, where is my, it's gone. Oh, no, sorry. We ended up adding this column, the quarter column, and we also ended up adding a column to identify each unique transaction. Okay, and then you can see that the main point that we were interested is to investigate the vendors. Okay. And the vendors are then classified by unique transaction identifier, the amount of money that the transaction represents, where the funds come from, what's the objective of that transaction, which agency in the state made the payment. and for what program. Okay, so we pick up that information. We pick up that information and go to the process of generating the model, okay, which is a texification. And I don't go into the details here, but once you have that texification, it goes into the DB2VEC generator, and you end up with a codified name for each one of the entries in the table and its corresponding vector. Okay? Let me skip this for the sake of time. This is the state of Virginia. Some of the information that's related in terms of counties and cities. This is the way the counties are divided. That's the population distribution. And the one thing that we're interested in this particular example was actually to look at education spending. Okay, so the state in 2016 spent $46 billion, approximately 5.3 million transactions, 191 unique customers, all the way from banks to individual persons, and they spend about half of the money is spent in education. Okay, and in here actually tells you published information about high school degree. So the maximum is 96.3% of the people in the county get a high school degree. The minimum is 65, and then they have similar statistics for bachelor's degree. Okay, and which you can see varies dramatically. So there's one county that has a 72% rate of people end up getting a bachelor's degree, and there is another county that only gets about 8%. Okay? So we start putting these SQL queries, and the next slides will show some examples of them. The first one is the similarity. Okay? So we went and picked up one county, the county of Arlington, just out of the blue. And if we run the similarity, and we end up with this reason. County of Hills, Caroline, and James City are the closest ones to County of Arlington. So we start looking at the specifics of the data, and County of Arlington has 87 transactions in the database. It deals with 2 agencies, 2 funds, 2 objectives, and 15 programs. And then the County of Hills has similar amount of transactions, 78. Not necessarily the same amount of money, but the important part is this. It deals with 3 agencies. 2 of them are common to the County of Arlington. It deals with 4 funds. 2 of them are common with the County of Arlington as well. And they are common for 74 transactions. Okay? So you do the analysis for each one of these entities, and you see that they are very common with each other, which would justify why these counties are close to each other. Okay. In the similarity, in the contrary, if you do the dissimilarity and give it the count of Arlington, then we're asking which counties are not similar to Arlington, and again, you have the same analysis that I did before, or we did before, and you can see that the other counties, have no transactions to any of the agencies, funds, objectives, or programs as the County of Arlington. Okay. Then we implemented this semantic lab, and what we wanted to know is Fairfax County is the largest county in the state in terms of population, and we want to know which counties were similar to Fairfax, okay, and which agents they dealt with, and what was the value that they dealt with. And without doing any analysis on the specifics of the agencies, we ended up with the Department of Education, okay, because majority of transactions for the public school for Fairfax County end up being not only other public school systems, but also the public schools associated with the counties that have the most population. Okay? We also did a similar analysis, but from comparing the quarters. So we wanted to know what does the Fairfax County Public School System spends in Q1, and which counties have that similar behavior to Fairfax County in Q1 and Q3, and we end up again with the counties on the top of the most. I guess I should have put this table there. So the most populous counties next to Fairfax County end up showing up here as well. And again, I think one of the points to emphasize here is that we never specified that we were looking at the Department of Education. Okay? I think I'm pretty much done. So I just summarized one use of a relational system that uses AI database, and created several semantic queries that can be used within SQL and can be used by any database, relational database system. Okay, sorry, it's pretty quick. That's all.
Thank you.